Now let us take some interesting compounds called annulenes. See, annulenes are actually the monocyclic and of course carbocyclic, nothing but homocyclic. Polyenes, I mean having more than one double bond. With alternate arrangement of the double bond. And of course, the single bonds. Okay, these are called annulenes. So they are monocyclic, having one ring, carbocyclic, ring is made of carbon atoms only. Of course, polyenes having many double bonds, and the arrangement of double and single bonds is, of course, alternate. Okay, let me take some examples. In fact, these are known things. Generally, we call this cyclobutadiene. But you know, this can of course be called 4-annulene. It has got 4 pi electrons. So it's called 4-annulene. And we know that this is anti-aromatic. Now, look at this. So this is of course benzene. But you know, in this particular terminology, we call this 6-annulene. 6-annulene, of course, is aromatic. Now, if you consider the cyclooctatetraene, what do we call this? It's called 8-annulene. Now, 8-annulene, of course, is anti-aromatic. Okay, so 4, 6, and 8-annulene. Next. The 10-annulene is very interesting. Look at this. 10-annulene. See, this 10-annulene can be given as this. Okay. Now, here the interesting point is it has got 10 pi electrons. Has to be aromatic. But see what the problem is. You have a hydrogen here and you have another hydrogen here. Now these two hydrogens will have steric or van der Waals repulsion. Okay. because of which the coplanarity is destroyed. The coplanarity of all the 2p orbitals is destroyed. They'll not be in the same plane, so that is how it becomes non-planar. Okay, non-planar, so is non-aromatic. You know, this is very interesting. It has 10 pi electrons, but still it is non-aromatic. But why? Because of the repulsion. You got steric or van der Waals repulsion, specifically known as transannular repulsion. Very important. Now, these transannular repulsions, in fact, they destroy the coplanarity of all the 2p orbitals. This is the issue, because of which it has become non-planar, so is non-aromatic. Though it has 10 pi electrons, it is non-aromatic. Look at the. But see, if suppose these positions, instead of keeping them as it is, if they are bridged this way, then of course the aromaticity can be retained. Look at this. Now the bridges are used up and the bridge is taken outside. The transannular positions, look at these two positions. These transannular positions are now bridged using an atom. Now this actually makes it planar. As a result, it becomes aromatic. Only change what we made is we have bridged. Bridging the transannular position it makes the molecule planar. So this is very important. We have just bridged it. And it has become aromatic. The next one. After 10 annulene, let's take 14 annulene. Now, this also is very interesting. Yes. This is 14 annulene. the alternate double and single bonds. Look at this. Now this molecule, again you got hydrogens having a kind of repulsion among themselves. So this repulsion, in fact, makes it predominantly non-aromatic. Very interesting. Mostly non-aromatic. But you know, at some point in time, when they are little away from each other, I mean for a shorter duration, it remains aromatic. This is the speciality of 14 annuli. Okay. It's predominantly, mostly non-aromatic. Only for a shorter duration, it becomes aromatic. Right. Now let me give you something much similar to this. It's pyrene. Look at the interesting part of this one. Just a note. It's not. Yes, it's not exactly the same, but a similar one. Look at this. There is a pi bond at this position. Now, interesting is, see, there are 1, 2, 3, 6, 8. I mean, you got 16 pi electrons, right? Has a total of 16 pi electrons. Point number 1. But the interesting part is this particular pair, you know, this is not involved in conjugation. So that is the interesting part. When this is not involved in conjugation, obviously it will have 14 pi electrons. Therefore, it becomes aromatic. Has to be known, that's it. The more you study, the more you go through different books, you find different examples. That's it. This is very interesting. Now, let us take 18 annulene. Of course, no big problem here. It's aromatic. 1, 2, 3, 4, 5, 6, 7, 8, 9. And the hydrogen. Take them this way. No doubt, even here also we expect a kind of repulsion, but that repulsion is not that heavy to make it non-planar. So it is planar. It has 18 pi electrons, therefore is aromatic, right? Now let us take some bicyclic compounds. Okay. The first one is, it is this. So this is called pentalene. Okay. And as we can see, it has 8 pi electrons and therefore is anti-aromatic. Okay. Next, very interesting. It's called Azulene. A very important and a very interesting example. Has some speciality. Look at this. A 5-membered ring and a 7-membered ring. Yeah, these are all bicyclic. Okay. 1, 2, 3, 4, 5, 6, 7. Right. Now this is Azulene. You know, Azulenes, there are certain other varieties of compounds called fulvalenes. These, of course, are said to be aromatic when we consider their dipolar structure. Now you can actually see this. Let me tell you in simple terms. This is a kind of cyclopentadiene, and this is of course cycloheptatriene, right? If this is made an anion and if this is made a cation, then they'll become aromatic. Both the rings will become aromatic. I mean, they have to be made dipolar. a plus, a minus. Okay, then they become aromatic. And this happens in excited state. But in the neutral molecular state, they generally are not aromatic. They don't actually seem to be aromatic. So this kind of a situation is called chameleon aromatics or chameleon state. Chameleon, I hope you know what chameleon is. Changes its colors, right? That is how even these also, they actually are aromatic in their dipolar state. Okay, now let me show you the dipolar state. As and when the bonds migrate this way, it develops charges. Let me show you that. Now see the position. See, this particular carbon has lost its bond. So let me put a positive charge here. And the bond migrates this way. Okay. Then this. And here you get a negative charge. Now I think it is very clear. You can clearly see the two things. Cyclopentadienyl anion and on the other hand, if you see this, it is like cycloheptatrienyl cation, nothing but the tropylium cation, right? Both are aromatic. So the dipolar structure overall gives it the aromaticity. Okay. And this dipolar structure is actually responsible. The high dipole moment, due to this structure, azulenes have high dipole moment, right? So this is about azulene, a very interesting example. Check this out. Next is, let us consider fulvalene. Let's see what are fulvalenes. These are actually the simplest non-benzenide conjugated hydrocarbon. As I said, even these doesn't seem to be, I mean, they don't seem to be aromatic under normal conditions. But when you consider their dipolar structure, they seem to be, or they seem to be exhibiting aromaticism. Now look at the example. Look at this. See, these are non-benzenoid structures. It's called calicine. Okay. Now let's see how it becomes aromatic. As such, calic means couple. Now let us take the resonance form of this one. See, there are of course two possibilities, but let us do this way. If it is taken this way, then we get a negative charge on this and a positive charge here on this carbon, right? Now it's very clear. This is our cyclopentadienyl anion kind of structure, which is aromatic. And look at this. This is, of course, cyclopropenyl cation, again aromatic. Now, this dipolar structure of calicine, which of course has a dipole moment of 4 dB, is aromatic. This is very interesting. Let me write a note here. regarding the azulenes and fulvaline, what I said earlier. See, the azulenes and the fulvaline, they are said to be exhibiting aromaticity due to dipolar structures in excited state. Whereas in a neutral molecular state, I mean, if you consider this, they do not seem to be aromatic. This is known as chameleon aromaticity. Chameleon. I mean, behaving in different ways. You know, that chameleon is the one which changes its color. So this is very interesting. Chameleon aromatics. Because they exhibit a dipolar structure in excited state and of course exhibit aromaticity. But in neutral molecular state, they don't behave as aromatic. Okay.